A scientist once described time as what stops everything happening at once. Of all the big questions of existence, perhaps none impacts on our daily lives more than the problem of time. There's never enough of it, of course. Here in the desert, the dream time of Australia's Aborigines collides with the linear time of European culture, leaving both communities puzzled and bewildered. Can science solve the riddle of time, or are we destined to remain eternally mystified? They sometimes call this the timeless land, Paul, but of course time is hanging heavy here, isn't it? It's making its commentary on the landscape. It's even making a bit of a commentary on us. I think it's time to talk about time. To what extent does it remain an absolute and utter mystery?
It's not an utter mystery, but our personal perception of time doesn't sit easily with our modern understanding of time through physics. There's a mismatch there, a clash, in fact a very violent clash.
You're not simply talking Greenwich Mean Time versus Eastern Standard, you're talking, say, block time versus the conventions.
I'm talking about something very deep, which is that in daily life we all have this overwhelming impression that time is passing. Time flies, as we say.
You're right, Paul, I've noticed that. Yes.
that it's moving, that things change. And our whole language, our way of thinking about the world is rooted in this idea of a flux of time. And yet, when we look in the laboratory to see what causes this flux, how we can measure this flux, there's nothing there. Time doesn't seem to move or pass at all. Now, that's not saying that there is no time, that time itself is an illusion. Certainly we can measure intervals of time. What we can't measure is the passage of time. And many philosophers and many scientists will argue that time simply doesn't pass. Our impression of the passage of time is an illusion.
Well, we've used the term counterintuitive before, but that's the big one. That's capital C, capital I.
That's the one that had me lying awake in my teens thinking, why am I living now? Why am I me? Is there a future? Does it already exist? What happened to the past?
What about your old pal Augustine? Does he have a crack at it in his theology?
Well, he does, in the sense that he can see the riddle that is there, and that is why he made this famous statement that we all know what time is until somebody asks us, and then we're lost for words. And the point is that time is rather special in as much as we feel it inside ourselves. It's in our very souls, isn't it? It's something that is...
Well, we have a clock in our chest, don't we, beating
but
away.
It's not a question of just the biological rhythms keeping us in tune with our environment. It's something that we actually feel. The passage of time is something that we can perceive internally in a way that we can't with intervals of space or mass or electric charge or any of these other physical quantities. Time has this special role. In fact, Sir Arthur Eddington, the old British astronomer, I think summed it up quite well by saying that it's as if we've got a back door into our minds through which nature's temporality creeps. We have a sort of privy view to time, whereas with other physical quantities we've got to get at them through our normal senses. But time's something that's inside us, and that's why I think people are so fascinated with the nature of time.
And terrified.
And terrified, because when we start saying, well, time is relative, or time doesn't pass, or time had a beginning and an end, it seems almost like a personal assault.
There was a time when there was one clock in the village in the tower, and it only had an hour hand. Then they added a minute. Now, of course, I've got a second hand on my watch. You've got one of those tricky little digital numbers which blinks away furiously. There are atomic clocks. It's as if technological determinism was making us more and more obsessed with time.
Yes, it wasn't always that way. You see, most ancient cultures didn't have any notion of precision timekeeping in the same way that we have today. They lived very much in tune with the cycles and rhythms of nature. It was almost a biological thing. Curiously enough, the Greeks, who did so much to turn geometry into a precise science and art, left time alone. And it was only with Galileo and Newton and what we would call the scientific revolution that this notion of time as an infinitely precisely measurable parameter came into currency. In fact, Newton's own words are absolute, true and mathematical time that flows equably without relation to anything external. The notion that time is something there as a sort of backdrop to the universe, ticking away with infinite precision. And it's just a matter of technology to be able to measure those time intervals as accurately as we would like.
But then along comes the guy with the Hypo Marx haircut, Einstein and blows that to smithereens.
That's right, absolutely. And that's the real revolution in our understanding of time, which has taken place this century. Now, Newton, you see, spoke of this time flowing equably, and so he, by extrapolation of common sense and ordinary experience, assumed that time had this flux, this
And
motion.
it could be now everywhere.
That's right, and that it was absolute, a universal time, the same time for everybody. Your time and my time are exactly the same. It doesn't matter how we move or where we are. There's only the time. Whereas Einstein demolished that whole set of ideas and showed that time is relative, to use the jargon, that your time and my time needn't be the same. They can get out of step, and they can get out of step in a very simple way.
Well, give a few demonstrations of this.
Yeah, well, I could, if I go off camera, though, because if I just stand up and walk about, that's all I need to do to introduce what we might call a time warp or a time dilation between your time and my time. Ordinary
A movement
motion.
as small as that.
Well, it's a very tiny effect. The faster you go, the bigger it gets. And to see it really conspicuously, you need to go close to the speed of light. And then time can be very severely dislocated or warped, one relative to the other. But nevertheless, even at sort of everyday speeds, it's a measurable effect. So, for example, if you go on an airliner and take an atomic clock as a passenger, when you come back to the ground and the clock is compared with its clone left behind at the airport terminal, you will find that there's a measurable discrepancy. It's a real effect. It's a small effect in the case of aircraft speeds, but it's measurable. We're talking about a few billionths of a second for a few hours worth of flying, but it's well within the capability of modern atomic clocks. So time really is warped by motion, and this leads to what is sometimes known as the twins effect, or sometimes called the twins paradox, though it's not actually paradoxical. Imagine a pair of twins. Suppose you and I are twins.
Hard to imagine,
You,
Paul,
you
but
decide
I'll struggle to do
sit
so.
here in Cooperpedy, and I get in my rocket ship over there and head off to a nearby star, close to the speed of light. And you sit here, and 10 years later, you're getting a bit impatient. But eventually the rocket ship appears, and out I step, and I don't seem to have aged at all. And you say, you've been gone for 10 years, so we're getting very impatient here. And I say, not at all. I've only been gone a year. My watch here says that I've been gone a year. I've got these accurate chronometers on the rocket ship. I really have only been gone a year. And the question is, who is right? Are you right? Has 10 years elapsed, or has 1 year elapsed?
Can I ask the question?
Well, the answer
Who
is
is
we're both
right?
right. We're both right.
Right, I thought you'd say that.
Because time is relative. Your time and my time are different because we're moving differently. So this leads to a very profound conclusion, because if you ask the question, having sat here patiently for, say, 3 years, well, I wonder what old Davis is doing up there now. Clearly, the question is meaningless in my frame of reference, because my entire journey is only going to take 1 year for your 10 years. So my now and your now have got out of kilter with each other just by the simple process of moving differently. And so
it'll be impossible, of course, to have a Greenwich Mean Time for the cosmos.
That's right. You see, and that's the whole point. Whose time are we going to take for this universal, this absolute time that Newton wanted? There isn't one. So the notion of there being a universal present moment throughout the universe that divides time into past, present and future is clearly a meaningless one. It's just been demolished. The experimental evidence shows quite clearly there's no common now. And I might say it's not just motion that causes a time warp. Gravitation can do it as well. Many people don't realise time runs a little bit faster up in space than it does down here on the surface of the Earth, because the Earth's gravity slows time. So if you live at the top of a high-rise building, time passes a little bit faster.
Does that mean that as it approaches a black hole, time would stretch almost to the infinite?
Yes, the surface of a black hole represents an infinite time warp. That if we could somehow position a clock on the surface of a black hole, which we can't do, incidentally, but if you can imagine it, then if we could observe that clock, it would simply seem to be frozen in time. In fact, black holes used to be called frozen stars in the old days, because time literally stands still there, relative to us here. Of course, if you went to the surface of the black hole, time would be much as it is anywhere. But comparing their clocks and our clocks, there's an infinite mismatch, an infinite discrepancy.
This may be a completely ludicrous question, but if you were to approach a black hole, would your perception of time change?
No. You see, the whole point is in your own frame of reference, time is time.
Right.
And it's only by doing comparisons between clocks or personal experiences in different frames of reference that you reveal the discrepancies. That's why we say time is relative. Your time, my time, can be different relative to each other. But nobody's right and nobody's wrong.
I now have to raise the difficult question, well, for me, impossible, of block time, getting back to the idea that that time doesn't happen?
Yes, it was Einstein's colleague Hermann Weyl who said that the world doesn't happen, it simply is. Einstein himself said that the past, present and future are only illusions, however persistent. And curiously enough, he said that in a letter to the widow of his friend Michel Bessot after he died.
Or to console the widow?
Yes. That,
I don't think that would be
in some
particularly
sense
efficacious, would it?
He hasn't passed on or passed away because time doesn't pass. So the physicist treats time in much the same way as the Greeks treated space. That is, it's a dimension. So we have dimensions of space, and we have 3 dimensions, maybe more, and 1 dimension of time. And it's simply there. It's laid out before us. I like to use the word the timescape. You see, we sit here and we're surrounded by the landscape, and there it is. It's laid out before us all around. Well, if we now regard time as something which is laid out before us, then that's the timescape. And so when the physicist thinks about the world, it's space-time as a 4-dimensional scape. And there are, of course, events, there are intervals of time, and we use clocks to measure those intervals of time, just as we use rulers to measure intervals of space. But nothing's actually happening. It's simply all there at once.
Well, Paul, I cannot escape the gravitational pull of the wristwatch or the pendulum, but there you are, the godlike physicist, gazing down on this timescape. And there it all is. Does that mean that the universe is predetermined?
Not necessarily. The fact that the future can, in some sense, already exist doesn't mean that it's completely determined by the present. So when Einstein said the past, present and future are only illusions, however persistent, what he meant was that there is nothing in physics to say that only the present is real and that the past has somehow slipped away into a half-reality whilst the future has yet to come into being. Because there's simply no way of chopping space-time, the timescape, up into this past,
okay,
present
except
and
that
future.
they're all equally real.
So
I
they've
can
got
see
to somehow all
that.
be there, you
Yeah.
see. And so now the point is, if we think about an event in the year, 2100 or something, is that event completely determined by everything that's happening in the universe at this particular time? That's what determinism means. It means that if you happen to know what everything in the universe is doing at one instant, that is enough, there's enough information there to be able to figure out what it's going to do at some future instant. That's what determinism means. And Newton's scheme, the clockwork universe, was a completely deterministic universe. The doctrine of determinism means that the future, in some sense, doesn't introduce anything new, that everything about the universe is already contained in its present moment. The Belgian chemist Ilya Prigogine, I think, summed it up rather nicely, that if the world was like that, time would be a gratuitous thing, just a parameter that fulfills no function. He said it's rather like God turning the pages of a cosmic history book that's already written. And so there's been a bit of a sort of rebellion against that way of looking at the universe. And of course we don't believe that it is deterministic. It's not actually like that.
To some extent, you'd argue, I guess, that the universe has a form of free will.
Yes, an openness. I don't like the word free will because I don't really know what it means in the case of humans.
You object to it in terms of a human application.
Yes, what I try to do is rather than trying to find something special about humans that injects this mysterious thing called free will into our actions, I try to find something in the wider universe that could mirror that human freedom. And it seems to me that there is an openness in nature in general. That even inanimate
Macro
systems,
to micro, it's there. Yeah.
Well, even inanimate systems, we now know from the theory of chaos, which has been so popular in recent years, that even in a system which is, in a strict mathematical sense, deterministic, nevertheless there are many systems, namely chaotic systems, that are so exquisitely sensitive to the initial conditions that the slightest change, the slightest error or perturbation will cause them to do something dramatically different, often called the butterfly effect. And so we know that even a system that might be, strictly speaking, deterministic, nevertheless is unpredictable. And human freedom, I think, has something to do with that lack of predictability.
What about time travel?
Yes, just as we can go to different parts of the landscape, driving around here, so we could perhaps visit different parts of the timescape. Now, travel into the future is a reality. We've just been talking about it. The twins effect is essentially time travel into the future. And the reason is that if I go off for my 1-year journey and you're stuck here for 10, I've effectively travelled 9
travel
years
into my future.
into your future. But I can't use that method to get back again. I can't just reverse my trajectory in the rocket and come back to the starting point. So time travel into the future, one-way journey, is a reality. We can do it. It's been done. We're doing it all the time, in a sense. But travel into the past is a much tougher proposition. Now, curiously enough, Einstein's...
Well, I prefer to travel into the past. I'm a bit more interested in that. So you're going to frustrate my ambitions. I can't go back to ancient Egypt and watch them putting up the pyramids.
Well, we don't absolutely know that, but it looks to be pretty tough, certainly very expensive. Einstein's theory of relativity, which is about the best thing we have to go on when it comes to the nature of time, leaves open the question as to whether it would be possible to visit the past. And I should explain right at the outset that this is not quite like H.G. Wells' famous story of the time machine, where somehow, by throwing a lever in a machine, you make the movie run backwards and then stop it at some stage. Time travel into the past, a la Einstein, is a bit like you travel in a loop in space, but you come back to your starting point before you left. Now, that possibility is left open, although in practical terms, most of the scenarios that have been explored look to be extremely fanciful.
Now, doesn't that open all sorts of paradoxes?
Well, it does indeed. I suppose the best known of the time travel paradoxes is sometimes called the grandfather paradox. Imagine if I was to go back 100 years or something and seek out my grandfather as a young man and shoot him. What then would happen? If poor old Grandad is dead, then Paul Davis would never have been born, but then Paul Davis could never become a time traveller, so I couldn't have gone back to commit the murder, and so on. We get into inconsistent nonsense. And this is always the problem with travel into the past as opposed to the future, because the past is connected to the present through causality. So if we go back and change the past, we change the present as well. And that's a really major problem for the whole idea of travel into the past. In fact, for that reason, Stephen Hawking introduced what he called his chronology protection hypothesis, making the universe safe for historians. And the hypothesis simply says that in some way nature must prevent us from travelling back into the past, even if it appears that the laws of physics will allow us to do it.
What happens if the universe does decide to collapse back along the lines we were discussing in the last program? Would that allow time to run backwards?
That's a different state of affairs. Travelling backwards in time and time itself reversing sound similar things, but they're actually logically different. Now, it's often been conjectured that the arrow of time, the fact that we see sequences of events that have a definite directionality to them, that arrow of time, it's often been conjectured, could reverse, go the other way. What would that mean? Well, we started out this episode by talking about the timeless landscape, you see, but of course it's not really timeless. If you took a movie film of that, then over a few million years you'd certainly notice changes. And if you ran that movie film in reverse, we'd all spot that it was running backwards. Conjectures about time running backwards are a little bit like that what they say is that is it possible under some circumstances for the movie to, as it were, run in reverse, for rivers to flow uphill, for broken eggs to reassemble themselves, for people to grow younger instead of older. It's a very appealing idea. It's a very ancient idea. It goes right back to ancient Greece. Plato wrote about these sorts of things.
And Gould and Hawking do now.
That's right. Now it's sort of been resurrected in its modern form by a number of people. Thomas Gould in the 1960s suggested that the arrow of time, the directionality of physical events, has something to do with the expansion of the universe. So that if the universe should start to contract again at some later stage, then this arrow would reverse and things would tend to run backwards. Then, of course, he quickly spotted that if there are any intelligent beings around in this collapsing phase of the universe, they wouldn't notice anything unusual. They wouldn't say, "Good heavens, everything's all running backwards. You know, I can remember tomorrow and predict yesterday," because of course their mental processes would also be reversed. So they would regard their phase of the universe as perfectly normal, and we would be the guys.
It raises tantalising problems for a race meeting, doesn't it? Do you think
Yes.
we're about to have one of those paradigm shifts that you've been describing in our regard to time? Given that Einstein's postulations are now getting pretty elderly, it's remarkable how little effect this has had on ordinary people who still insist that time's winged heels...
You know, it is astonishing. I've recently written a book on time and been travelling around the world just giving lectures on the subject. And during that time, talking about things which have been pretty standard stuff for physics undergraduates for decades, results which are now 90 years old, nearly 100 years old. And people are still absolutely astonished to learn of things like the twins effect.
Well, the trickle-down effect is going to take more time, isn't it? But you're right, we hold on to our concept of time because it's built into us.
We've still got this essentially Newtonian view of the universe, of time as something absolute and universal. And people give that up very reluctantly. And it's because, of course, in daily life we don't notice these weird time warps and time dislocations. But if we were to move at close to the speed of light or through intense gravitational fields, we'd become very familiar with this dislocation of time.
And will that happen, do you think? As you think into the future, as you follow the arrow, do you think our technologies will ever allow us to?
No, not in our lifetime.
No, certainly not. You've once described Einstein's greatest mistake as being related to time.
Yes, Einstein very curiously introduced something into his general theory of relativity in the very early days, back about 1916, 1917, which might well account for the discrepancy that we were talking about in an earlier episode between the age of the universe and the ages of the stars, the oldest stars. Let me remind you that the oldest stars seem to be about 14 or 15 billion years old, but the best guess at the age of the universe, based on the Hubble Space Telescope data, give it an age of perhaps no more than 10 or 12 billion years. It seems that this idea of Einstein can be used to reconcile these two numbers. Now, Einstein, curiously enough, when he first constructed a model of the universe, of course he was unaware it was expanding, and he assumed that the universe would be static and eternal. And it's very strange, actually, because he must have known about the second law of thermodynamics and the fact that the stars can't have been burning for all eternity. Yet he went ahead and tried to find, within the scope of his field equations, of his general theory of relativity, a way of making the universe static. Now, in cosmology, the only force in town is gravitation. Gravitation is a pulling force, an attractive force, and therefore, inevitably, if you have a static universe and let it go, it's going to collapse in on itself. Big crunch. If you want the universe to be static, you have to combat that attractive force with a repulsive force. So Einstein introduced into his theory of relativity a repulsive type of gravity, an anti-gravity, if you like, to balance the attraction of the gravitational force. The problem is that this was unstable. It only needed someone to sneeze, and the entire universe would either collapse to a big crunch or head off on a sort of runaway expansion. And so partly for that reason, and partly because Einstein then discovered to his chagrin in 1931 that the universe is expanding, and he realized that from developing this static model of the universe, he'd missed a trick. He could have actually predicted the expansion of the universe if he'd stuck to his guns and kept to the original formulation of the theory. He dropped this cosmic repulsion term in disgust, calling it the greatest mistake, greatest blunder of his life. But curiously, it's had a bit of a resurrection in recent years. It now turns out that some sort of cosmic repulsion, some sort of anti-gravity, is an inevitable byproduct of some of the other forces of nature, for example, the nuclear forces. So what Einstein threw out the front door has come back in through the window. And the reason that this can fix up this timescale discrepancy is because if there really is some sort of large-scale cosmic repulsion abroad in the universe, then it is going to affect the rate at which the expansion of the universe slows with time. And that in turn will, of course, affect the relationship between the present rate of expansion of the universe and the inferred age. So my own preferred resolution of this age discrepancy is that Einstein was right all along and that his greatest mistake could yet turn out to be his greatest triumph.
Well, if time doesn't really pass, how come we've run out of it so quickly? If the relationship between time and consciousness is confusing, then consciousness itself is the ultimate conundrum. What are minds? Are we the only truly conscious beings in the universe? Could a computer be conscious and have feelings? Some of the topics to be tackled in our next episode, when we'll ask, is there a ghost in the machine?